Hello, my name is Thomas Shukla. This is Lab 1 Physics 2012 at Georgia Tech. Introduction. The aim of this lab was to measure and model the balance between gravitational force and electrostatic repulsion between two charged pieces of tape. Some of the fundamental concepts involved was consider each charged tape to be a point charge and ignore air drag and charge leakage during the experiment. One of the other fundamental forces was the electrostatic force, the Coulomb's law. That is, the electrostatic force is equals to QE Q1 Q2 over R squared. That's the magnitude of the electrostatic force. Gravitational force Fg is equals to mass times the gravitational constant g, which is 9.81, and floating of the charge table occur under equilibrium. That is when gravitational force equals electrostatic force. Charge quantization. So the net charge of the tape comes from a deficit or surplus of electrons. Charge relates directly to number of elementary charges, where the smallest unit of elementary charge is E equals to 1.6 times 10 to the negative 19 coulombs. Setup. For this experiment, two equal strips of clear tape are cut and suspended. One piece is fixed while the other piece is free to move, and both are charged are quickly pulling tape from the surface. So you have two tapes, you have one on the other, you tape one on the other while one's taped to the surface, and you pull the other, and that charges the tape. Now, how you proceed with the experiment is you have these two strips, and you suspend one by fixing it on some sort of surface, and then you bring the other one right next to it. So the original position, as you can see in the figure, will be slack, but when you bring will be like slack because it's going down like that. But when you hit it at one point, it goes up because of the repulsion, and it floats essentially, right? So the things you want to measure: the length and width of the tape, the mass of the tape, and the equilibrium distance between the tapes when floating occurs. A computational model setup. So tapes are really approximated as point charges located at the centers. There are two forces on the upper tape: there's gravitational force and electric force to charge lower tape. For equilibrium, both forces must be equal in magnitude and opposite in direction. So assumptions: you treat each charged piece of tape as a single point with all charge and mass concentrated at that point. Air resistance or drag is really negligible, and it wasn't factored into calculations. Also assume that all the charge in the tape was uniformly distributed across the tape. The glow script code. This is the glow script code. In the beginning, we initialize all the constants needed. Define G force, E force, define Q, charge per tape, print some stuff, print the two spheres, G force, E force again, and yeah, the arrows obviously then, yeah. This is the actual result. So you have two spheres. The orange is the force upwards, is electrostatic force, and green is the force downwards, is gravitational force. They both equal each other out. The results is charge per tape is 1.5 times to the negative 8 coulombs, so that's very less. Electron deficit is 9.5 times to the negative 10 to the 10, yes, and that's the atoms with electrons. So discussion. So what if the electrons had positive charge was a negative charge? So what would change is already the labels of positive and negative are just arbitrary conventions. And if we swap the signs, that is, we call negative, positive, positive, negative, really changes nothing except the language you use. All force interactions would remain the same. Like charge will still repel, opposite will still attract. The tapes will still repel each other and float in the same way, because then they just be the opposite charge of what we call it right now. So why is it important to handle the charged tapes as little as possible? What happens when they come into contact with hands or other objects? So human skin and most obviously conductive, or at least partially conductive. So touching the tape provides a path for charge to leak away. It's called grounding. That just reduces that charge on it. So charge can also redistribute evenly if the tape touches other surface, like if it touches surface, so that changes experiment results. So also oils and moisture, it increases conductivity and accelerates charge loss. So really just do not touch it to prevent charge loss and to get the best result possible from the experiment. Some of the sources of error. So uneven charge distribution. So one of the assumptions we have was a uniform charge along tape, but in reality it may clump in patches, so that's uneven charge distribution. Air currents or vibration. The small drafts can shake up the experiment and alerting the distance measured. Charge leakage. Tapes may lose charge quickly when touched. It's while they're only contacting other surface. So again, that's charge leakage. We don't want that. Mass estimate. We use 1 gram per meter. That's the guideline we use. But really, it's uncertain sometimes. Like it may be here or there. So measurement uncertainty. So difficulty precisely measuring the separation distance between tapes when they just start floating. So if you don't get the distance down to pretty accurately, obviously your final results can be flawed. So that's the sources of error. Anyways, that's it for lab one. It was amazing lab. It was fun. So thank you. Tamay Shukla signing out.